Hello everyone, welcome back. In this video we're going to talk about an application of the tangent line, which are called linear approximations. So let's consider the graph of a function y equals f of x and its tangent line through the point a comma f of a. So the red curve here is our function and the blue line is the tangent line through the point a comma f of a. Now, if we were to zoom in towards this point, we obtain the graph on the right. And we notice that the function looks very close to the tangent line near the point of tangency. And so we can use this observation to approximate the values of the function when x is close to a. So the idea behind linearization is that we can calculate the exact value of the function f of a quite easily, but it is rather difficult to calculate values of the function when x is close to a. So rather than using the function to approximate or to find the values that are close to a, we can use the tangent line to approximate the values instead, because it's a lot easier to work with the tangent line than it is with the function itself. And so we can define the linearization of the function as follows. So the linearization of f at a is given by this equation. So L of x is equal to f of a plus f prime of a times x minus a. And really, this is just the tangent line at the point a comma f of a. If you were to use the point slope formula, where the slope of the tangent line is the derivative evaluated at a, your x1 coordinate would be a, and your y1 coordinate would be f of a. This is really just the tangent line through that point. So let's have a look at some examples of finding linearizations and then using them to approximate certain numbers. So let's consider the function f is equal to the square root of x plus 3. And let's find the linearization at the point where a is equal to 1. So the linearization is given as f of a plus f prime of a times x minus a. So for our case, a is equal to 1. So the linearization at this point is equal to f of 1 plus f prime of 1 times x minus 1. So what we need are the two values, f of 1 and f prime of 1. So let's first calculate f of 1. F of 1 is the square root of 1 plus 3, which is the square root of 4, which is equal to 2. Now we need to find f prime of 1, and to find f prime of 1, we first need to find the derivative, f prime of x. So let's first rewrite the function as x plus 3 to the power of 1/2. We can then use the chain rule to calculate the derivative. So we have 1/2 times x plus 3 to the power of negative 1/2. And then chain rule says we multiply by the derivative of the inner function, which is equal to 1. So now rewriting so that we don't have any negative exponents, this is 1 over 2 times x plus 3 to the power of 1/2, which is 1 over 2 times the square root of x plus 3. So now we can calculate f prime of 1, which is 1 over 2 times the root of 1 plus 3, which is 1 over 2 times the root of 4. So that is equal to 1 over 2 times 2, which is 1/4. So now we can use this to find our linearization. So the linearization of our function is equal to 2 plus 1/4 times x minus 1. So now we can use this linearization to approximate the numbers, the square root of 3.98 and the square root of 4.05. So now our function is given as the square root of x plus 3, and we want to approximate the value of root 3.98. So now what I need to determine is the value of x that I want to use so that the function gives me a value of root 3.98. So what does x need to be so that if I evaluate the function at this coordinate, I will get root 3.98. So if x was equal to 0.98, then f of 0.98 would be the root of 0.98 plus 3, which is equal to root 3.98. So this tells me that x has to be 0.98, and then we can use this to approximate this value by substituting this into our linearization. So the function f is going to be approximately the linearization at this x coordinate. So we can evaluate L at 0.98, and this will give us the approximation to root 3.98. So L of 0.98 is 2 plus 1 over 4 times 0.98 minus 1. And so this would be 2 plus 1/4 times negative 0.02. And so as a fraction, we can write this as negative 1 over 50. So that is 2 minus 1 over 200, making a common denominator of 200. We get 400 minus 1 over 200, which is 399 over 200. And so the approximation to root 3.98 is 399 over 200. So here's the graph of the function root of x plus 3 and its linearization, which is the tangent line at the point 1, 2. So the exact value of root 3.98 is given as this decimal expansion here. So here's the exact value of the function at 0.98. We use the linearization to approximate this value. So again, we evaluated L at the x coordinate of 0.98, and the approximation is 1.995. So we see this is a fairly close approximation to the exact value. So let's also approximate the square root of 4.05 by using the same linearization. So again, if our function is the square root of x plus 3, and I want to approximate the value of root 4.05, then what x coordinate do I need to use so I get the square root of 4.05? Well, if I substitute 1.05 into the function, then I get the square root of 1.05 plus 3. And that will give me root of 4.05. And so that tells me that we can use the x-coordinate of 1.05, and we can approximate this value by using the linearization instead. So we substitute 1.05 into the function of L, then we get 2 plus 1 over 4 times 1.05 minus 1. So that is 2 plus 1 over 4 times 0.05. So that is 2 plus 1 over 4 times 1 over 20. So 2 plus 1 over 80. So that is 160 over 80 plus 1 over 80, which is 161 over 80. So here the exact value for the square root of 4.05 is given by 2.01246117975. And so we can use the linearization to approximate this value. So we evaluate the function L at 1.05, then the approximation is going to be 2.0125. And again, we notice that this is a fairly good approximation to the exact value. Now, are these approximations over or under estimates of the exact values? Now, if we didn't know what the exact values were, we can still determine whether the approximations are over or under estimates of the exact values based on where the tangent line is on the curve. Notice that the tangent line is sitting above the function, and because we're using the tangent line's values to approximate the function values, we know that these approximations are going to be overestimates. If the tangent line was sitting below the curve, then the approximations would be underestimates. So because the tangent line is sitting above the function, we know that our approximations are going to be overestimates. So let's have a look at some examples of finding linearizations. So let's consider the function x to the power of 3 over 4. And we want the linearization where a is equal to 16. So the linearization is f of 16 plus f prime of 16 times x minus 16. So what we need to look for is the function evaluated at 16, as well as the derivative evaluated at 16. So we have 16 to the power of 3 over 4, which is the fourth root of 16, all to the power of 3. The fourth root of 16 is 2, and 2 cubed gives us 8. So f of 16 is equal to 8. Now we need to find the derivative. So using the power rule, this is 3 over 4 times x to the power of negative 1 over 4. And we can write this as 3 over 4 times x to the power of 1 over 4, or this is 3 over 4 times the 4th root of x. So now we can evaluate the function, or the derivative, at 16. This gives us 3 over 4 times the 4th root of 16. So that's 3 over 4 times 2, or 3 over 8. And so the linearization is 8 plus 3 over 8 times x minus 16. In the next example, we have f is the sine of x, and we want the linearization at pi over 6. So L of x is f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So let's first find f of pi over 6. This is the sine of pi over 6, which is 1/2. Next we need the derivative. So f prime of x, we know that the derivative of sine is cosine. We can now evaluate the derivative at pi over 6, which gives us the cosine of pi over 6, which is root 3 over 2. And so the linearization of sine at pi over 6 is 1/2 plus root 3 over 2 times x minus pi over 6. Now in the third example, let's use a linear approximation to estimate the given number. So let's first approximate e to the power of 0.015 using a linear approximation. So here what we need to determine is the function f of x, as well as the value of a, where we want to find our linearization. So there are many different functions that we can use to define the linearization. So one function we could use is e to the power of x. Now we also need to determine the value of a. Now when we're determining the value of a, we want to pick a value such that we can find the exact value of the function at this point. And this value has to be very close to what we're trying to approximate. So in this case, the value of a should be very close to negative 0.015. And we also want to make sure that we can evaluate the function quite easily. So what value of a should we pick? Well, if we choose a to be 0, then I know that f of 0, which is e to the power of 0, is equal to 1. And so we should choose a to be equal to 0, since we can evaluate the function quite easily at this point, and it's very close to negative 0.015. So now we can find our linearization. So that is f of 0 plus f prime of 0 times x minus 0. So we can evaluate f of 0. which is e to the 0, or 1. F prime of x is the derivative of e to the x, which is e to the x. And the derivative evaluated at 0 is e to the 0, which is 1. And so the linearization L is going to be 1 plus 1 times x, which is 1 plus x. So now we can use this to approximate e to the power of negative 0.015. So we need to determine the value of x such that it will be equal to e to the negative 0.015 when I substitute it into f of x. So if we choose x to be negative 0.015, then that gives us e to the power of negative 0.015. And so our x value is going to be negative 0.015. So now we can use this to approximate the value by using L of x. So we substitute negative 0.015 into the linearization. Then we get 1 plus negative 0.015, which gives us 0.985. So in the next example, let's approximate 1 over 4.002. So let's first determine our function as well as the a value for our linearization. So one possible function we can use is the reciprocal function, 1 over x. And we also need to determine a value a for our linearization. And again, we want to choose a value so that it will be close to what we're trying to approximate, which is 1 over 4.002. But we can also evaluate the function quite easily, so we can determine its exact value. So if you choose a to be 4, then we know that f of 4 is 1 over 4, which is 0.25. So we can use 4 as our a value in the linearization. And so L of x is going to be f of 4 plus f prime of 4 times x minus 4. So finding f of 4, we get 1 over 4, which is 0.25. And then to find f prime of 4, we first need its derivative. So using the power rule, we have negative 1 times x to the negative 2. So that is negative 1 over x squared. And then evaluating the function at 4, we get negative 1 over 4 squared, which is negative 1 over 16. So now we can use this to determine the linearization, which is 1 over 4 minus 1 over 16 times x minus 4. So now let's use L of x to approximate 1 over 4.002. So if the function is 1 over x, then what value do I need In order to get 1 over 4.002, when I substitute this into f of x, well, if we choose x to be 4.002, then we get 1 over 4.002. And so the x value that we want to use is 4.002. So now this will be approximately L of 4.002. So we substitute that into L of x, we get 1 over 4 minus 1 over 16 times 4.002 minus 4. So that is 1 over 4 minus 1 over 16 times 0.002, and this will be 0.249875.